thank you for putting up this conference and give me an opportunity to talk about my research. Thank you, Andrew. Thank you. I know you had a really hard time to try and pronounce my name, so I know it's really hard, it's long, but you prefer calling me the last part of the first name, I'm fine. Call it Raja, I'm fine with that. So, just to introduce myself, I'm doing my third year of my PhD program in University of Waterloo, Applied Math. I'm working with Dr. Customers. And before I proceed, I'd like to thank Dr. Customers for her support right through my work. So here I am, going to give a short talk about optimal actuator location for H-infinity control. So actuators are like physical control devices. So the bigger picture is I'm trying to find like possible location to place these actuators, and I'm also considering the H-infinity control criteria. So again, the bigger picture of this is like you want to minimize the effect of disturbance onto the system. So I'm going to give a good background about the H-infinity control as well. Here is a brief outline of what my talk is going to be mostly, and so I'm going to come up with a lot of examples and try to motivate why this problem is interesting. Secondly, I'm going to give you a brief overview of what H-infinity control is about. And lastly, the problem that I'm currently working on is optimal actuator location for H-infinity control. I've got some theoretical results as well as numerical results, and I'll go over that. Here's a quick example. So, vibration control and noise control are sort of very famous traditional applications which are looked up by control engineers. On one beam, we consider like a simply supported beam, which are fixed at these two ends. So basically, the deflection is 0 at those two ends, and also the moment is 0 at those two ends. And here it's like a actuator, so it's like a point actuator. So now you have like a freedom in placing this actuator all around the beam, right? So which sort of a location is like optimal that gives you the best performance? So that's the question here. On a 2D structure, you could think of a plate. So this plate is like clamped at this end, and these black patches that you see are called the piezoelectric actuators. So the idea behind these actuators are, these are like electromechanical devices. So based on the mechanical vibrations, they convert into useful electrical pulses. So the idea is to, where do you want to place these actuators such that you get the best optimal performance? So again, the performance could be classified in many ways. I'll go over that later. So the bigger picture is, well, you could think of the flight wings. So notice that these wings are basically like a 2D plate, not rectangular in size, shape, but something like a 2D plate, which is fixed at this end and the other end is free. So you automatically have vibrations in the plate. And here is a better picture that basically is like a laboratory setup where they basically want to find out the optimal location to place the actuators. So these white patches are basically those piezoelectric actuators. Another application is in civil engineering. Often people do this. So on this really high-rise buildings, they want to keep the actuators at certain heights, so that it doesn't always work, but they basically want to make sure that the building is not shattered because of an earthquake. So engineers have done this. They have basically taken the data from previous earthquake excitation and run the data with respect to the control that they identify over this problem. So another application is the noise control. So think of constructing like a soundproof room. Say for example, you are sitting inside a flight. There's a lot of noise made outside the flight because of the engine and whatnot, right? So sitting inside the flight, you definitely don't want to hear all those noise. So the idea is, here is a like prototype of that problem. So you see a white color box here. So there is like noise made outside the box, and the noise is measured at the inside. So what people do is they place actuators around the periphery of this block, so then they can reduce the amount of noise heard inside. So again the question is, where would you want to place these actuators? So there are two critical stages to this problem, and the first one is basically the fact that all these vibrations are modeled by partial differential equations. So the vibrations in this plate is usually like a PDE, right, which is clamped at one end and the other end is free. So notice that it's required to identify the state space correctly, because often these PDEs, the state space is usually infinite dimensional, solid Hilbert spaces. However, like what usually the researchers have done is they've approximated that problem and they basically converted the PDE into a ODE, and then they solve the optimal actuator location problem on the approximated problem. Right? So basically these M, V, R, K are like the mass matrix, the damping and the stiffness coefficient. So the V of R is sort of how the control comes into the problem. So this is what is done since 1980, and people have solved this problem, but they mostly worked with the approximated problem, not really with the original problem. So the real question is the solution for the approximated problem valid for the original problem. So I talked about how to come up with these specific the performance requirements. So that basically depends on the problem that we are working on. So it's more specific for that corresponding problem. But in general, I identified that there are three most commonly performed strategies available in the engineering literature. The first one is like the controllability. So based on the controllability of the system at a particular location of the actuator, so they come up with another objective function and they go about finding the optimal actuator location for that problem. The unfortunate thing about this problem is like it only gives you like the actuator location, but it doesn't give you the control along with it. So it's just like an open loop criteria, and it doesn't give you the control. So we would obviously not like to do that. So we would look for some criteria where we could do both the optimal actuator location problem and the control problem. We want to like solve them simultaneously. So that's the goal here. And there is a very good thing about this strategy, the linear quadratic control strategy. So the bigger picture is like you want to minimize the effect of the energy of both the input and the output. So the good thing about this is it comes with the control. Like people have talked about in this conference before about linear quadratic control and how you end up with an Picard equation and whatnot. So the good thing about this is you have a control along with the optimal actuator location problem. And I'm interested in this criteria, the H-infinity control criteria. So again, so you basically have some disturbance coming into the picture, and you want to have the minimal effect of the disturbance on the system. So since 1980s, people were more interested in coming up with a suitable objective function. So they tried many different objective functions, and most likely most of them fall under these three criteria. So how do you go about finding the optimal actuator location? You basically come up with an objective function defined by this, which is parameterized with respect to the location of the actuator, and you find the optimal cost by finding the infimum over all possible locations. Like very natural thing to do. And also the location that corresponds to that minimal cost is going to give you the optimal actuator location. So my choice, as I said earlier, I want to pick H-infinity control criteria, and also my supervisor of the custom models has published results on linear quadratic control. By that I mean she basically developed the mathematical theory for finding the optimal actuator location for linear quadratic control, but it is not available for H-infinity control yet. So my idea here is like I'm basically developing the theory for H-infinity control criteria. So before I talk more about H-infinity control, like a very brief background about that. So I'm considering our usual system Z like on a Hilbert space, the state of our system, and in our problem A is usually like a partial derivative operator, and B and D are like the input and the disturbance operators. V of t here is signifies the